Okay, we'll get underway. Welcome, everyone. My name is Emma Kerr. I'm the General Manager of Marketing and Events here at Ostmine, and I'm happy to be your host today. Before we begin, I'd like to acknowledge that I am hosting the webinar from Perth on the traditional lands of the Whadjuk Noongar people. I also acknowledge the traditional custodians of the various lands on which we all work today and the Aboriginal and Torres Strait Islander people who may be attending this webinar. So welcome to everyone. I am today joined by Michael Zolotov, Chief Technology Officer and co-founder of Razor Labs, who will be presenting shortly. This webinar is being recorded and will be available to all attendees. It will also be posted on Ostmine's YouTube channel in the coming days. At the conclusion of Michael's presentation, there will also be a live Q&A session. You can submit your questions at any time during the presentation using the Q&A button at the bottom of your screen. So without further ado, I would like to hand over to Michael to commence his presentation. Over to you.
Thank you very much. And thank you for our friends in Ostmine. Let me share the screen and we can commence. Fantastic. So it's a pleasure to be here, and thank you everyone for attending this webinar. Our goal is in this webinar to discuss our methodology for diagnosing mobile fleets and for performing predictive maintenance for mobile fleets, and specifically our methodology in Australia. I'm going to start with really a very brief introduction about myself and about the company. And from there, we're going to dive straight into the content of the webinar and into our methodology. A bit about myself and about the company. First of all, it's a pleasure to be here. I'm the Chief Technology Officer of the company. I'm also one of the co-founders. I established the company with my partners a bit more than 10 years ago. And my background before that is deeply involved in machine learning and deep learning, while in the last 10 years is applying machine learning and deep learning solutions for the mining industry, applying artificial intelligence solutions for the mining industry, meeting stakeholders really from the reliability engineers and production engineers on site and up to executives and COOs and so on, and really working across multiple commodities and multiple geographies. The company that we established developed a very unique technology that we call AI sensor fusion. I hope that I can also use here the laser. So AI sensor fusion, and this is the technology that we're going to present today. We're a publicly traded company, went directly from bootstrap and up to being publicly listed. We IPO'd for $150 million a few years ago. And we have global presence, not only in Australia, but also in North America, South America, Africa, and Europe. We work today with very large companies such as Glencore, such as Yancoal, NGF, Cymec, and many others. And even more than that, we have a lot of experience in different commodities. So we have different experience in diverse operations, from iron ore to gold to copper to vanadium, chromium, coal, of course, both globally, working in basically all continents today, but also in Australia, working across diverse commodities and diverse from underground to surface operations, processing plants, and basically every type of site that I can imagine. Now diving straight into what we're going to discuss are the mobile fleets. The mobile fleets in mining these are the challenges that we're trying to solve. The mobile fleets in mining are, first of all, very expensive, and they have a tremendous impact on the maintenance cost of the operations, and of course, also impact on the unplanned downtime in these operations. We can see that the operator behavior has also a tremendous impact on the mechanical longevity of these components. They have a tremendous impact on how many times these components would need to be replaced. And these are, of course, very expensive replacements. And many times, many sites just lack visibility into their mobile fleets, from visibility into the even most basic failure modes and the failure codes, and up to, of course, visibility into the full telemetry and the data that's coming from these vehicles. When we started working in this field, we looked at what the current solutions offer. And the current solutions, I'm of course generalizing here, but most of them are based on a very simple, basically every sensor has a single threshold. If that threshold is crossed, I have an alarm. And this is a very, or too simplistic of a solution because first and foremost, it causes a tremendous amount of false alarms. And I guess every site experiences this one. It can be hundreds and hundreds of critical alarms per day that the team on site is expected to investigate, which is, of course, not practical. Also, I need an expert in order to investigate these alarms because the expert needs to actually go themselves into the data if they have access to the data in order to understand what is really happening and how do I create the right work order for that alarm. And again, imagine there are hundreds of these per day. What happens is that many of these alarms are actually very, very late. And in that point of time, very expensive damage is already caused to that component. Whether it's a part of the engine or the transmission, that component would actually need to be replaced already, even if that alarm is acted on right now. And lastly, many of these operator behaviors are not visible in these simple alarm because there are much more sophisticated patterns in the data. We've seen these drawbacks and we've basically built a product, and I'm going to now go into the methodology of how it works in order to give an answer to these drawbacks. So first and foremost, we asked ourselves, how would a professional work? What would be the methodology of a professional reliability engineer? And their methodology is not to look at one sensor with one threshold, but rather to look holistically at the data, to combine everything and to analyze it all together in order to give a diagnosis. So we understood that our product needed to work exactly that way. Our product, first of all, looks at all the sensors that are coming from the vehicles. We're going to speak about it, but it means that we have a way of extracting all the data from multiple OEMs. But these sensors, not only that are looked all together and analyzed all together, but they are also combined with the oil analysis, with the coolant analysis, with the fuel analysis, in order to, of course, cover more issues and to give another perspective of the condition of the machine. We're also looking at the maintenance data, right? That free text that can be English, it can be Spanish in other sites or Portuguese and so on that tells us exactly what the technician has seen, what was done, what kind of a repair was performed, and all of that is combined together. Also, tire information where it's available, and of course, dispatch information that allows us to also cross-reference it with the operators of that vehicle, so we also understand what operators drove when and what kind of operator insights can be extracted. All of these are combined together to give three deliverables in our methodology. The first one is the ability to detect things and issues much earlier. We're speaking here about many weeks, in many times more than a month, before there is any OEM alarm in the vehicle. And that basically means that if that is acted on, that repair would be much cheaper because it's, of course, much cheaper to lubricate something or to align something than to replace the entire component. And this is the goal here. Second of all, it's not telling a symptom like a temperature is above 100, but rather a true diagnosis. We always use the analogy of a doctor, a true diagnosis of failure mode, what is the root cause, what is recommended to be done, and this is done across all the different components of the system. And that saves very precious investigation time of the team that can now be focused on actually resolving the issues rather than chasing these alarms and doing all the investigations manually. So this is today done by the AI. And of course, the operator behavior, which allows us to track dozens of different types of behaviors that are basically ruining the vehicle and are shortening the lifespan of its components, such as the engine, transmission, final drive, suspensions, and so on. And all of that is done basically 24/7. So the AI runs all the time. It's tracking the data that's coming from the vehicle and from the laboratories, and it's basically giving this analysis continuously, so no failure is missed. So this is our high-level methodology. I want to now dive into the AI. How does it work? and basically what it delivers and our methodology around this one. So we have basically very easy few steps. The first step is getting the data. Basically, when we look today at the amount of data that's already there by the OEMs, it's tremendous. Most vehicles have about 100 sensors already installed on them, coming like that from the OEM. Not always the clients have access to the data, but the sensors are nevertheless there. It ranges from about 70 sensors on older vehicles to more than 200 or even 300 on newer ones, already there placed on the vehicle. If I'm taking an average of about 100 and I have 100 vehicles in my fleet, it means that I have 10,000 new data points generated every second that can be monitored, right? Even if I'm looking at only the amount of fault codes that are generated today by mostly OEMs, I'm looking at hundreds and hundreds per week. In that site example, we have about 700 critical alarms per week, about 100 per day that the team on site needs to look at. That specific site has 3 condition monitoring engineers, which is, of course, not realistic to investigate 100 alarms per day, critical alarms. By the way, if I would look at non-critical ones, we're speaking here about many thousands per day, which is, of course, not realistic, and basically many alarms and many failures just slip through and turn into actual breakdowns. So we get this data, and instead of doing all of this manual work, we've basically built an AI in order to analyze that data. And we're speaking here about one of the uniqueness points. We have two major uniqueness points. This is one of them. And the uniqueness point here is that we've seen many older AI systems takes a tremendous time to teach and to train and to establish baselines and thresholds and so on. And we don't need to do it in our system. This AI already comes with all the mechanical knowledge that's required in order to diagnose an issue. And the analogy that we use here is of a doctor. Imagine that you went to a doctor and you needed to teach your doctor medicine. It would not be considered such a good doctor, right? Because not only that you need to invest so much effort and time into teaching your doctor, but you would also be dependent on the failures that you've seen in the past. You could not diagnose any new stuff in the future. And the goal here is to build a huge library of models of anything that can go wrong in these machines and to work from day one. This of course required a tremendous development and R&D from our team that we completed. And we have today models for all major OEMs, from Caterpillar to Komatsu to Sandvik to Epiroc, basically Hitachi, all major OEMs today in the market, that when we plug a machine into our system, that's it. The system is up and running and giving diagnosis of that machine. And these diagnoses are not a simple sensor is above 100 because anybody can do it, but rather a much more sophisticated, as you see here, cross correlations and so on between the sensors that allow us to deliver several different, I would say, several different fields. So what is the failure mode? What is the root cause? And what is recommended to be done? And I'm going to give, of course, several examples, but this is delivered today across all failure, all deteriorations in the vehicle. So the team on site exactly knows what to do. I'm going to, of course, show an example. But we do not stop there because the diagnosis is not enough. Our goal is to basically push the issue to the full resolution, right? I mean, to really close the loop here. And the loop is only closed when the issue is repaired. And therefore, what we do is we have weekly meetings with the site where, first of all, we go through the new diagnosis. Our experts explain to the site answer any questions that are required to open a work order. And when the work order is actually closed, the AI would rerun automatically, would make sure that the issue was truly resolved. And if it's not, we would actually help the customer to understand what were the gaps or what are the next steps that are required to fully resolve the issue. We integrate into SAP or any other CMMS, so all the work orders are fully synchronized together with the CMMS that the customer uses. And this methodology of tracking the diagnosis right from the inception through the life cycle in SAP or whatever CMMS the customer uses, but also verifying the repair of this issue through AI and through experts that are there to answer also questions, because we need that human interaction, of course, as a part of the process and the management of change, are, from our experience, the best methodology to achieve the full resolution of the issue and the true closure of that issue and the extraction of the value. And this is done today across, as I said, all OEMs and also different types of vehicles. While we historically started with haul trucks, we we then advanced to loaders and to excavators, of course, both underground, on the surface, ADTs, and basically any type of vehicle. We support today all major OEMs and, of course, also manufacturers of engine and so on. And the system is accustomed to all of them. I want to give now maybe a few examples of what does our AI do differently, and then in the remaining time, speak about how do we extract the data and our methodology there, and then we will finish. So I want to give a few examples of how it is different from what the OEMs do today. And this is a real example of a Caterpillar vehicle, in fact, that is having engine cooling system issues. On the left side, you can see a healthy vehicle. And I'm showing you here two sensors. I'm showing here the coolant temperature that you can see going up and down, and the fan speed of that engine that is a part of the mechanism to cool the engine. And you can see that once the temperature goes up, the fan speed is working, the fan is working harder, and so on and so forth. You can see the correlation. In that vehicle, this is already a vehicle that has a problem. You can see that, first of all, the coolant temperature is higher, but the fan is not working as hard. Right? There is a problem in that system. You can see in both cases the same alarm off, in this case, Caterpillar. The alarm is set to 107 degrees. In both of the cases, we didn't get to the alarm level. But it is very clear for a human to see. If I would show that graph to a human, any human would very easily see that the correlation here broke. And this, of course, is indicative of a failure that, of course, needs to be diagnosed with the rest of the sensors and the oil and so on. But this is something that can be seen many weeks before that threshold would be crossed, before there is damage to the cooling system and maybe other parts of the engine itself. In the Caterpillar simple threshold case, everything is okay. The threshold was not crossed, everything is okay. In our case, because we're looking at these correlations, we can already say, guys, this vehicle is deteriorating. These are the root causes, and this is what needs to be done. And this is a very simple example, only two sensors that we look at together. Imagine more complex examples where you have 3 or 4 or 5 or 6 such sensors. It's not uncommon, and we're able to find these patterns much earlier. Now, of course, a person can theoretically do it if I show the specific place in the graph and so on. But imagine having 100 such graphs for each and every one of your vehicles, and you have 100 maybe vehicles or 50 or whatever it is. It is impractical to, of course, do it manually on site. I'm taking the same example, the same coolant example, on a different vehicle. And again, we have the same 107-degree alarm that is never crossed. So for Caterpillar in this case, but it's really the same for other OEMs, that vehicle is completely healthy. But what we see here is that the entire fleet that is shown here as gray lines is in a certain area because of their operations and their environment and so on. But that vehicle is much hotter, right? So we can see that in comparison to that fleet, that vehicle is in a worse condition that does not characterize the rest of the fleet. This would trigger inside our system an investigation, of course, done by the AI that would deliver, of course, a root cause of that issue, of that deterioration, and of course, the recommended actions. So again, this is an example of a vehicle that for the OEM would be completely normal up until it's too late. But in our case, again, many times more than a month before, would already trigger a deterioration that's shown in our system, in our platform, and would deliver the full diagnosis and the full recommended actions for this case. Last case that I'm going to now touch before I go to the hardware side and how do we extract the data is false alarms, right? So we discussed false alarms, and I'm going to give you here an example of one of the reasons why OEMs have so many false alarms when you use a simple methodology of a single sensor and threshold, right? We have here the air filter restriction. It's of course the filter in the intake of the engine. And in that case, the vehicle was not, and we have here the ground speed. In this case, the vehicle was not even driving, and there was a high RPM burst basically done by the operator. And because of that burst, we can see that restriction values that were completely nominal and completely okay just spiked literally for a few seconds, crossed the thresholds, and once that high RPM burst went away, it got back to normal. So in a system that just puts one threshold, we would have here 10, this is another case of Caterpillar, we would have 10 false alarms just generated because of this single event. In a system that looks at all of the data holistically, it is very easy, and of course, to a human expert, it is very easy to see that there is nothing here because the vehicle was not even driving. The vehicle was either at the shop or was either, in another place that, again, was not even driving, and you can also see it in the rest of the telemetry. So our ability to take all of these sensors and combine them to also suppress these false alarms and to give context to the true alarms that we see and the true deteriorations is much more powerful because of that methodology that we chose. And this is basically done, as I said, for all of the different components of the vehicle. And we have today thousands and thousands of models that are really covering every failure that is known to us. I want to now speak a bit about how do we extract the data from the vehicle, because one of the things that we see is that sites many times do not even have access to the telemetry and sometimes even to the focals of these vehicles. And for that, we've built a data logger. The data logger basically connects. It's a robust device that connects to the internal network of the vehicle. And this is our second uniqueness factor. We were able to decode all the telemetry of all major OEMs in the market. And the way that it works is that, first of all, we perform a site survey. In the site survey, we understand what is your vehicle, what is its type, what's its serial number. We have a huge library of vehicles that we are interpreting. And basically, the way that it works is that we connect to the service port of the vehicle, and we basically, there are several, in many cases, several networks of CAN bus that we connect to. And basically, whether these are regular CAN bus, what's called J1939, or whether it's the Caterpillar proprietary network called the CDL, the CAD Data Link, or any other vendor, in Komatsu, it's ComNet and others, we're able to connect to that network. We never, of course, send any commands or anything like that, but we just get the data, and we are connected to an antenna that sends the data to the cloud via either Wi-Fi or LTE. And not only that, but we also have the ability to record the data on the device, because sometimes there is no reception. It might be an LHD underground that I'm now recording for even a whole day up until there is a single point of sight where there is reception, and that's completely fine, because remember that if I'm predicting here stuff a month into the future, it's okay for me to give my recommendation in that LHD case in the end of the day because I had no reception. It becomes less important at what hour did I give my prediction if it's so far into the future. So the way that it works is that that data that is extracted from the vehicle is combined in a very easy manner together with the rest of the data sources that we discussed, whether it's the oil and the coolant analysis or the work orders that are just easily ingested into our cloud via just simple CSV files. And then all the data is combined. All of the data is, importantly to say, of course, delivered to our customers, right? So our customers can, of course, have full access to the data. They are, of course, owning the data. So this is how it looks like within our system. They have full access to the data. They can download the data. They can integrate into the data and everything. But very importantly, this data then becomes a full-blown diagnosis of the issue that is written in pure, simple English text of what was found. The AI actually explains its reasoning behind the diagnosis and its methodology, and of course, the recommended actions. And as I said, this is done across all the different OEMs. This is an example from, for example, from a Caterpillar or an underground LHD. You can see that, of course, different vehicles have different compartments to connect to their internal networks. Sometimes it's below the driver, sometimes it's behind the driver. It really depends. In Komatsu, for example, excavators, it's again, there are different places for that. And usually our methodology is that we come for a site survey, we establish exactly the best place, we connect to the telemetry to also show the customer what data can be extracted, because as I said, the sensors are already there. There's nothing else needed to be deployed. Usually it's a work of about 2 or 3 hours per vehicle, depending, of course, on the configuration. And that's it. Basically, once this is done and that data logger is installed, the system is up and running and is showing all of the diagnosis that I've just mentioned. So there is no setup that's required from the customer. As I said, there is no anticipation of teaching us. We do not, by the way, use the customer's data to train our models because the models are already trained. So that also makes integrating to tier one miners and their cybersecurity concerns much easier. And that's basically it. I'm going to maybe touch now on the last issue of how do we track the value. So the system itself tracks every deterioration that was found. So the left side of the table, what was the vehicle, what was the component, the failure mode, what was found and what was recommended is tracked specifically independently by the system. And the right side of the table, which includes the KPIs that were agreed by the customer, whether it's the downtime, whether it's the spare parts cost or the parts cost and so on, are basically filled by the site team. And then whether if we perform a pilot or a full-blown implementation, it's very easy to track the ROI because we have exactly every deterioration that we found, every failure that we found, and what was the value that was assigned to it by site. And this also allows us to separate from other improvement programs that the site might have been doing. Because if we were just looking at overall downtime or overall maintenance costs, of course, there are many factors that can influence it, not only us and our system. Once we track specifically the cases that we found and that were truly resolved by the site, then it's a much easier methodology to track the overall value of the system and, of course, the ROI on that one. So this is basically our methodology. As I said, to sum up, we have two uniqueness factors. One is the data logger that allows us to decode, interpret, and extract all the data from all the telemetry, even proprietary ones from basically all OEMs, all major OEMs today in the mining sector. And of course, the second one, which is our AI engine that is able to diagnose as a true doctor these issues many weeks, in many cases, more than a month before they actually translate into real failures. And this is our uniqueness factor today. And that's basically it from my side. I will stop here and to give you a chance to ask questions.
Great. Thanks so much, Michael. That was a fantastic and thorough presentation. Just a reminder to the audience, if you have any questions, you can pop that into the Q&A box at the bottom of your screen. Just to kick off the questions, I do have a question for you, Michael. So as we know, many mining operations have mixed OEM fleets. So how does Data-Mined AI handle data from different manufacturers using their own proprietary formats?
Yeah, it's a good question because these sites have even more complexity. Imagine that a site, for example, that has only Caterpillar fleets would need Caterpillar experts. If I have two or three or even more OEMs, because I have also underground loaders and haul trucks and excavators and so on, it would mean that I would need also many more experts that are very hard to find for for the condition monitoring and reliability of my fleet. Because we support all OEMs today, inside our system, you would actually see all your mixed fleets. You would see your Komatsus, your Caterpillars, your Epirocks, your Sandviks, your Hitachis. It would all be in a single place. And all of the diagnosis would be normally delivered inside. So a mine site with mixed fleets that is struggling to find these experts, or that these experts are not enough to cover the huge amount of vehicles that they have, now have much more powerful tools to basically reduce all that noise that is coming from the alarms, because right now they need to chase hundreds and hundreds of these alarms, and to basically concentrate on the true deteriorations that are seen in the data. And imagine that this AI, as you've seen, exactly writes in text what it found, and of course gives the accompanying graphs. And then they can focus on actually doing these actions and thinking about the more strategic maintenance activities rather than just chasing and investigating each and every one of these alarms.
Great, thank you. We do have a question from the audience. So the question is, what's a realistic lead time and how far in advance does the system typically flag a failure before it would have occurred?
Sure. So I would say two things. First of all, it of course depends on the failure, right? If you have a lubricant or an oil leak, you will have increased friction, and that can even deteriorate over 2 weeks. But if I'm looking at the average, usually we're speaking about at least a month, so that even if something becomes, so we have 4 levels of criticality in the system. We have green, yellow, orange, and red. Usually, when something becomes orange, this is when we actually give actual recommended actions. And in that state, you would actually have more than a month in order to resolve that issue. And it means that in that case, you would create a work order. In a planned one, it would not be in some panic mode. In many cases, it would actually be more than a month, but I would say that a month and a half is roughly the average lead time.
Excellent. And
I
another
would, by the
question.
way, add that many failures are not necessarily also finishing in some catastrophic failure, but many of them are just reducing the lifespan of that component, right? So that component can still work for multiple months into the future, but you want to do this, lubrication or whatever the action is there in order to just prevent damage to that component and to its surrounding components. So that's also uh, uh, um, one of the consequences, potential consequences of not doing an action.
Excellent. Thank you. Another question from the audience. So what does deployment typically look like and how quickly can an operation get up and running?
Sure. So just like I've shown, we have basically 3 steps. In the first step, we come to a site survey. A site survey typically takes between half a day to a day on site, depending on the amount of different vehicle types. We need access to just a single vehicle of every type that is in the pilot. Usually we start with a pilot of about, let's say, around 10, 15 vehicles, depending on the site operations and the diversity of its fleet. So we come to site for half a day or a day. We connect to each and every one of the vehicles. We see that the data is extracted. We show it to the customer, and we plan exactly where the antenna would go, the logger, and so on. It's basically half a day on site. And then that's basically it. I mean, we schedule the deployment of across the vehicles with the site. Some sites want us to come to several concentrated days and to basically deploy the entire fleet. As I said, it's about 2 to 3 hours per vehicle after that site survey. Some other sites have very specific times where these vehicles are out of production, and then we come kind of surgically to deploy at these times. But basically, every vehicle that the data logger is deployed on, literally, you see them in the system on the next day with the diagnosis. So there's really nothing more than that. As I said, we usually start with a pilot of about 10 to 15 vehicles, depending on the vehicles on site. And then after the pilot, that usually takes between, let's say, 3 to 6 months, we can then expand to more vehicles and so on. Sometimes it already happens during the pilot itself.
Excellent. And we've got some great questions coming in from the audience. So another question we have is, how do you overcome network coverage challenges underground from transferring data from underground equipment to your analytics platform?
Yes, so it's a good question. I touched on it a bit while I presented. We are aware that underground there is no continuous reception, and it of course makes sense. The data logger itself would record the data while there is no reception. We do recommend that at least once per day or once per several days, there would be a place with reception. It can be Wi-Fi or LTE, but any kind of internet, basically. It can be a proprietary network, but a network that would allow the data logger to basically send the data to the cloud. The data logger has plenty of storage in it. It can record and record for long periods of times. If every day or every few days there is a place with reception, that recording would retroactively be sent to the cloud, and then you would see, of course, the data in the system and with the proper diagnosis and so on. Like I said in the webinar, imagine that if I'm giving here a prediction a month into the future, and because you didn't have reception on, during Tuesday, you only got the prediction on Tuesday evening, it doesn't matter so much because we're looking so far here into the future.
Excellent. And one more question from the audience. How do you keep training data up to date? OEMs are making changes in their health data from time to time.
Correct. So, of course, if I guess that the question is more for newer models and so on, we have, of course, R&D teams that are all the time updating our kind of medical textbooks and our library of models to accommodate for new and for newer and newer models. It's done continuously all the time. They're also doing research work, even to look at older models and try to find even milder, and more complex patterns that are indicative of these failures. So this is something that is done continuously all the time. We do need to remember that eventually you can break down the vehicles to three main categories. You have the mechanical ones, electrical ones. Now we have also battery electric and hydraulic ones. So there are a lot of similarities in the way that they work, but of course there are specifics for every vehicle, and that's why we have the R&D team that's their day job.
Perfect. Okay, thank you. I don't think we've got any more questions. So if anyone had any more questions, you can pop that in quickly now. Otherwise, I think we'll wrap up the webinar. So, Michael, thank you so much for your time and your passion today. It was a fantastic overview. If anyone has any questions or would like to follow up with Michael, please don't hesitate to reach out. We can certainly put you in contact with Michael and the Razor Labs team. So thanks again, Michael. And just a reminder that the webinar was recorded today, so we will share the recording with all of the attendees, and it will also be uploaded onto our YouTube channel. So given we don't have any more questions coming in, I'd like to just wrap up there. So thanks again for joining us, and we hope to welcome you all to another Osmind webinar soon. Thanks so much, Michael.
Thank you. It was a pleasure. Thank you very much.
Excellent. Have a great day, everyone.